Imagine a world where the ocean's tiniest scavengers tower over their distant cousins, Antarctic amphipods that would dwarf anything you would find closer to home. In seas hovering near -1.8 degrees Celsius, beneath 4 months without sunlight, these invertebrate giants thrive while most life slows to a crawl. What combination of freezing water, endless darkness, and pulsed summer feasts could produce such enormous creatures? And why are their future prospects suddenly at risk? The answer lies hidden in the frozen dark. A typical amphipod in temperate seas is easy to miss, barely a few millimeters long, a translucent speck sifting through sand or clinging to drifting kelp. But in Antarctic waters, something extraordinary happens. Here, amphipods can grow 2 centimeters, 3 centimeters, even 5 centimeters in length, dwarfing their relatives from warmer coasts. Imagine a crustacean the size of a fingernail, or in some species nearly as big as a child's hand. These are not isolated oddities. Antarctic seafloors are home to a whole cast of oversized invertebrates, sea spiders with legs stretching up to 70 centimeters, isopods as big as dinner plates, and worms thicker than a human finger. This pattern has a name: polar gigantism. It describes the tendency for many Antarctic marine invertebrates to reach sizes that would be impossible, or at least extremely rare, in more temperate oceans. Among them, the amphipod Waldeckia obesa stands out as a local heavyweight. In the cold, oxygen-rich shallows and under the sea ice, it cruises the benthos up to 3 centimeters long, 2 or 3 times the length of similar amphipods found in northern waters. In fact, about 1/3 of Antarctic amphipod species surpass double the average size for their genus, compared to less than 1% in the tropics. The sheer scale of these creatures rewrites expectations for what small seafloor animals can become. And yet the question remains, what is it about the Antarctic that allows these giants to thrive while their cousins elsewhere remain tiny? The mystery of polar gigantism begins with this striking contrast in size, a clue that something in these frozen seas is rewriting the rules of life below the ice. Seawater on the Antarctic shelf hovers just above its freezing point, around -1.8 degrees Celsius. For most of the year, a thick lid of sea ice covers the surface, locking the ocean beneath in a world of deep cold and perpetual twilight. The sun can vanish for nearly 4 months at a stretch, leaving the seafloor in darkness from late autumn through the heart of winter. When light finally returns, it comes in a sudden burst, triggering a brief but spectacular bloom of phytoplankton under the melting ice. This explosion of microscopic life rains down as organic particles, fueling a pulse of productivity that sustains the entire ecosystem. Scientists describe this as a feast and famine cycle, where the timing and magnitude of the summer bloom set the rhythm for life below. In these waters, the cold is not just a backdrop, it shapes every aspect of survival. The ocean's stable, near-freezing temperature means that chemical processes, growth, and even decay all run at a slower pace than in warmer seas. The thick sea ice and extended darkness limit the influx of energy from the sun, making the brief summer bloom a critical event. Yet even in the depths of polar night, the seafloor community remains active, relying on the reserves built up during the light. This extreme environment, cold, dark, and pulsed by sudden abundance, forms the stage on which the puzzle of polar gigantism plays out. The question is not only why Antarctic amphipods grow so large, but how these harsh conditions shape the very rules of life at the bottom of the world. Cold Antarctic waters hold a secret advantage. They are saturated with dissolved oxygen, far more than warmer seas. At temperatures near -1.8 degrees Celsius, oxygen molecules linger in the water, making these polar seas among the richest on Earth in terms of available oxygen. In laboratory tests, this difference is striking. 1 liter of Antarctic seawater can carry nearly twice as much oxygen as the same volume from temperate regions. For marine animals, this extra fuel changes the rules of survival. But oxygen is only part of the story. In these frigid conditions, every chemical reaction inside an amphipod slows down. The biological pace, from heartbeat to cell division, ticks at a fraction of the speed seen in warmer waters. Biologists call this the Q10 effect. For every 10-degree drop in temperature, metabolic rates are cut by half or more. In practical terms, an Antarctic amphipod's body uses oxygen more slowly, burning energy at a glacial pace. This slow motion metabolism means less oxygen is needed at any moment, but with so much available in the water, even large bodies can be supplied without running short. The oxygen temperature hypothesis, first proposed by physiologists studying polar invertebrates, suggests that this unique pairing, high oxygen outside and low demand inside, creates a window for gigantism. In the Southern Ocean, amphipods and sea spiders have grown to sizes that would be impossible in warmer, oxygen-poor habitats. As one scientist summarized, cold water holds more oxygen, and slow metabolism means you can get away with being big. The logic is compelling. The freezer at the bottom of the world acts as both a storehouse of oxygen and a natural brake on life's tempo, setting the stage for giants to thrive. Yet as research continues, it is clear that oxygen alone does not hold all the answers. Other forces are at work beneath the ice. Antarctic seas are often described as a world with the oxygen dial turned up, but the story of polar gigantism is not that simple. While cold water can hold more dissolved oxygen, the deep freeze brings its own complications. Inside an amphipod's body, oxygen does not flow freely. It must move molecule by molecule through layers of tissue. In very cold conditions, this process slows down. For a small animal, the journey from the surface to the inner cells is short. But as body size increases, the distance grows, and the slow pace of diffusion in cold tissue becomes a real barrier. Even in oxygen-rich water, the largest invertebrates risk running short if their tissues cannot keep up with demand. Physiologists have tested this idea by measuring how well giant Antarctic amphipods and sea spiders absorb oxygen. The results show that beyond a certain size diffusion alone cannot supply enough fuel, especially during bursts of activity. Some species compensate with thinner, more porous exoskeletons or increased surface area, but these adaptations have limits. In the largest animals, even these tricks may not be enough. This means that oxygen availability sets the stage, but it does not write the whole script. Ecologists add another layer to the puzzle. The Antarctic shelf is home to far fewer shell-crushing fish and crabs than most temperate seas. Without a gauntlet of predators, invertebrates can afford to grow slowly and reach larger sizes. This predator gap acts like an island effect, allowing giants to emerge in relative safety. At the same time, competition for food is shaped by size. Big amphipods can muscle out smaller rivals when a carcass lands on the seafloor. The consensus among scientists now is that polar gigantism comes from a blend of factors. High oxygen, slow metabolism, reduced predation, and the physics of diffusion all interact. No single explanation fits every case. Instead, the Antarctic is a living laboratory where multiple forces combine to stretch the limits of animal size in the cold and dark. Summer brings a sudden flood of light and life to the Antarctic shelf. As phytoplankton blooms under the melting ice, a rain of food drifts down, and amphipods like Waldeckia obesa gorge themselves. building reserves for the leaner months ahead. When autumn arrives, the light fades and the feast slows, but activity does not stop. Through the long polar night, these scavengers keep moving, combing the sea floor for scraps, dead jellyfish, stray algae, the occasional carcass. In darkness that lasts for months, they rely on the energy stored from summer's bounty. Spring's return of light triggers another ramp up, and the cycle begins again. This slow, steady rhythm, fueled by bursts of abundance and patient foraging, gives these amphipods the time and resources to reach sizes their temperate cousins never see. Antarctic shelf waters are changing. As temperatures rise and fresh meltwater spreads, dissolved oxygen is slipping away, and models project a loss of 10 to 15% in some regions by the century's end. For giant amphipods and their kin, this means tighter oxygen budgets, just as their physiology is already stretched by size. At the same time, king crabs and predatory fish are moving in from the deep and from warmer seas, crossing thermal barriers that once kept them out. Where giants once thrived in cold, oxygen-rich, predator-light waters, they now face a world with less air to breathe and more jaws to avoid. Today, Antarctic giants face shrinking oxygen and rising predators as the climate shifts. Their survival depends on a balance now tipping out of reach. These creatures remind us, when the rules of nature change, adaptation isn't guaranteed. What disappears in the dark may never return. Thank you for watching.